So before we proceed, let's do a bit of housekeeping and bring in some notation. So let's imagine I have a population here, and the size of the population, let's put it here, the size of a population has the notation uppercase N. So this is the size. The mean or the average of a population is this Greek symbol called mu. It's like you spell it M-I-O-U, mu. The standard deviation that I mentioned earlier, let's put it in standard deviation. For a population, that is, we're looking at right here, the standard deviation is notated by the Greek S. It's a circle with a line coming out to one side. That's actually known as sigma. S-I-G-M-A is the small sigma, not the large sigma. And then finally, if we square our standard deviation, so sigma squared, it's a related measure called the variance. So we have all those figures again for a sample. So if we have a sample here, the size of the sample is lowercase n. The mean of the sample is an x with the bar on the top. The standard deviation of a sample is just s. And the variance of a sample is just s squared. So that's some useful notation for us to know. So let's now go back to try and figuring out what is the standard deviation. So just a little recap. The standard deviation, I'll give you an example in fact. Standard deviation, let's do it with GPA scores again. Let's do it here. So this is a class I've got, average GPA score is 3. I've got 2 students and they both have exactly 3 GPA score. Got another class, average GPA score again is 3. But this time I have a student with a 2.5 GPA and I have another student here with a 3.5 GPA. So the average 2.5 and 3.5 is in fact 3, and the average here is also 3. They both have 3. So what's the spread from the center point? How spread out are these students in this first class? How spread out are they from the central point? The more spread out they are, the bigger the standard deviation. The less spread out they are, the smaller the standard deviation. In this particular case, they're not spread out at all from the central point, so I would expect my standard deviation to be equal to 0 for this class. There's no spread. They're not spread out. They're sitting right on the mean. Standard deviation is how spread out we are from the mean. On the other hand, these guys, if the mean is 3, this guy's spread that way, and this guy's spread this way. So there is a spread here. The answer should not be 0. So I want to find out, on average, how far are these data points away from the mean. So we can work it out here. You can use this formula here. Xi is a data point, and I want to find out how far away it is from the mean. That's what I want to find out. So let's work this out. So the first data point, the first student's 2.5, their GPA. And how far are they away from the mean? The mean is 3. And so this student is negative 0.5 units away from the mean. The negative means they're below the mean. Let's look at the second student. This student has a GPA or an X of 3.5. How far are they away from the mean? That's going to equal plus 0.5. When I try to take the average of these two figures, I'm going to get 0 because the plus and the minus cancel each other out. But 0 means there's no spread. It means they're sitting on the mean. So that's quite clearly not the case here. So that negative sign is actually causing some problems. Two ways of getting rid of the negative sign. One way is to take the absolute value and treat everything as positive. But the way that most people do it is they square this value. They square these values. And when you square these values, this comes back positive, this comes back positive, and then when we work out the average, we're going to get an actual value other than 0. When that's not actually working out the average. To work out the average, what we have to do is we have to take out xi, and we have to subtract the mean, and we have to square, and we have to sum out over everything. So that's the Greek summation sign that you see. So add up this guy squared plus this guy squared, and then we're going to divide by the population size. And because we've squared, though, it's not actually giving us the standard deviation that we wanted. It's giving us a measure that is squared. So to actually get back to the standard deviation, we're going to have to take the square root of that, because that squaring changed us into the squared unit. So this is the actual formula for working out the standard deviation if you have a population. So you can see I'm using mu, n, and sigma. I'm using mu, n, and sigma because I'm dealing with population, not a sample. And by the way, if I just had this part of it without the square root, so let me write that over here. So sum of xi minus the mean squared over the population size, that would actually be the standard deviation squared, and that is known as the variance. Now the variance we're not really using in this course other than to help us get to the standard deviation. We prefer to use the standard deviation because the standard deviation is in the same units as the actual question that we're dealing with. So if I work out, for example, that the standard deviation is 0.5, it means that the spread is 0.5. On average, one of the students is 0.5 GPA units away from that central location. It's in the same units, in the same GPA units, or whatever the question we're looking at is about. Now, this was all population data. What happens if it's sample data? Well, for sample data, things look fairly similar, but not exactly the same. I'm going to use S for the variance of a sample. S squared is the variance of a sample. S on its own is just the standard deviation of a sample. So this is going to be the variance. And I might as well put in sample to differentiate. So when I'm dealing with the sample data, like I did up here in purple, I'm talking about the sample. So I'll change the color code as well there. So this is the sample stuff here. The formula is going to look similar to the one above, but not exactly the same. It's going to be the sum. That's the same of xi. That's the same. Minus. But now we only use samples when we don't have the population data. So in here, I'm going to have to use x bar squared. And that adds in another complication, which I'm not going to divide by the sample size. If you remember up here, the sample size is n. I'm not going to divide by n. I'm going to divide by n minus 1. And the reason we divide by n minus 1 is this. We're not using the true population figure for the mean. We're using an estimated figure because it's not available. The population one is not available to us. So we have to be consistent now in all the calculations that we do. Any samples that we pull, anything that we do must average out to whatever this sample mean we put in here is. it has to now be consistent. So let's just say, for example, that this sample mean, we worked it out to be 10, that x bar was 10. It's not the real figure, but in the absence of having the real population mean, we're having to use the sample mean in its place. So if I was to now, for example, pick a sample of 3 numbers, this number, and this number, I have to ensure that when I add them together, if I'm picking a sample of 3 and divide by 3, they must average out to 10. So basically, if I was picking out a sample of 5, I must make sure that the average of those 5 numbers comes to 10. So I have to make sure that this fake figure I've put in, I'm consistent with. So when I go out to pick a sample of, say, 3 in this case, I'm very free to choose this number. I go in, I choose a number, let's suppose it comes out to 12. Great, free to choose that. And then I go in and choose another number, and it comes to, say, 10. That's fantastic. I chose that number freely. I just randomly went into my population and chose this figure. But this figure is not free to choose because these guys have to average out to 10. I already got 12 plus 10 is 22. This figure, this last figure, whether I want to or not, it has to be 8. I'm confined. It has to be 8. I have no freedom in choosing that. If it was anything other than 8, it wouldn't average out to 10. So even though in this case I've got n equals 3 pieces of data, 1, 2, 3, I'm only free to actually choose n minus 1 of them, which in this case 3 minus 1 is 2. I'm only free to choose 2 of them. So this is why we divide out by n minus 1. Every time we put a constraint on the calculations where we introduce a figure which is not the real figure, it's an estimated figure and it's a constraint, that constraint will reduce our flexibility in choosing numbers, and for each constraint we lose 1 degree of freedom in our choices. So if I was to have a second constraint, this would be n minus 2. But for now, this is all we need to know, that it's n minus 1. And the actual standard deviation for the sample, I can tell by this symbol that standard deviation is going to be the square root of the thing to the left. This will be the square root of this, the sum of xi minus x bar squared divided by n minus 1. Okay, so this is the standard deviation. So this is the standard deviation. I just put SD, the standard deviation of a sample. And just to finish off, this was the variance of a population. And this is the standard deviation up here. This guy up here, this up here is the standard deviation of a population. So familiarize yourself with population and sample, and you can just go back and look at this. So this is the items that we use if we have a population, and if we have a sample, these are the equivalent items that we use. So when we look at it, we know exactly what it is that we are referring to. We can differentiate between the standard deviation of a population. It's going to be this. It's going to be this figure up here. This is standard deviation. Population. This will be the standard deviation of a sample.